Analog Chebyshev filters are of two types, Chebyshev type 1 filters and Chebyshev type 2 filters. Chebyshev type 1 filters are all-pole filters. They exhibit equiripple behavior in the passband and monotonic behavior in the stopband. This is shown in the figure. In the passband, you can see a small ripple and no ripple in the stopband. Whereas Chebyshev type 2 filters contain both poles and zeros. They exhibit monotonic behavior in the passband and equiripple behavior in the stopband. The design of a Chebyshev filter requires the use of a formula absolute value of h of j omega whole square is equal to 1 upon 1 plus epsilon square cn square omega by omega p, where epsilon is the parameter of the filter related to the ripple in the passband and cn of x is the nth order Chebyshev polynomial defined as Cn of x is equal to cos of n cos inverse of x when absolute value of x is less than equal to 1, that is the passband, and Cn of x is equal to cos hyperbolic of n cos hyperbolic inverse of x when absolute value of x is greater than 1, the stopband. The Chebyshev polynomial is also defined by the recursive formula Cn of x is equal to 2x into Cn minus 1 of x minus Cn minus 2 of x when n is greater than 1. What is to be noted here is C0 of x is equal to 1 and C1 of x is equal to x. Now, because we have a recursive formula, using C0 of x and C1 of x, you can find C2 of x. From C2 of x and C1 of x, you can find C3 of x, and so on. The properties of Chebyshev polynomial are also available, where Cn of x is equal to minus Cn of minus x for n is odd, Cn of x is equal to Cn of minus x for n is even, Cn0 is equal to minus 1 raised to power n by 2, Cn0 is equal to 0, Cn1 is equal to 1, Cn of minus 1 is equal to 1, Cn of minus 1 is equal to minus 1. Cn of x oscillates with equiripple between plus minus 1 for absolute value of x is less than equal to 1. For all n 0 is less than equal to Cn of x, absolute value of x is less than equal to 1 and absolute value of Cn of x is greater than 1. Cn of x is monotonically increasing for absolute value of x greater than equal to 1. Shown in the figure is the characteristic of Chebyshev polynomial 1. So what happens is, if you really see, even though there is an equiripple, it starts at 1.0 when n is equal to odd, and it starts at 1 upon square root of 1 plus epsilon square when n is even. What is to be noted is the poles of a Chebyshev filter lie on an ellipse as opposed to a Butterworth filter where they lie on a circle. The formula for calculating the order of a Chebyshev filter is given by n is greater than equal to cos hyperbolic inverse of square root of 10 raised to power 0.1 alpha s minus 1 by 10 raised to power 0.1 alpha p minus 1 divided by cos hyperbolic inverse of omega s by omega p. This can also be written as n is greater than equal to cos hyperbolic inverse of lambda by epsilon by cos hyperbolic inverse of omega s by omega p, where epsilon is equal to 10 raised to power 0.1 alpha p minus 1 raised to power 1.5, lambda is equal to 10 raised to power 0.1 alpha s minus 1 raised to power 0.5. Now that we have two types of filters, the Butterworth filter and the Chebyshev filter, it is in order to do a comparison between the two. What you need to note is the magnitude response of a Butterworth filter decreases monotonically as the frequency omega increases from 0 to infinity, whereas the magnitude of response of the Chebyshev filter exhibits ripples in the passband or stopband according to the type. The transition band is more in Butterworth filter when compared to a Chebyshev filter. The poles of the Butterworth filter lie on a circle, whereas the poles of a Chebyshev filter lie on an ellipse. For the same specifications, the number of poles in a Butterworth filter are more when compared to a Chebyshev filter. The order of a Chebyshev filter is less than that of a equivalent Butterworth filter. Now we go to the steps in the designing of a Chebyshev low pass filter. From the given specifications, find the order of the filter, round it off to the next highest integer. Using the formulas for the values of A and B, the minor ellipse and the major ellipse have to be calculated. What are the formulas? A is equal to omega p mu raised to power 1 by n minus mu raised to power minus 1 by n by 2. B is equal to omega p into mu raised to power 1 by n plus mu raised to power minus 1 by n by 2. So what is mu? Mu is epsilon raised to power minus 1 plus square root of epsilon raised to power minus 2 plus 1, where epsilon is square root of 10 raised to power 0.1 alpha p minus 1. Omega p is equal to passband frequency and alpha p is equal to maximum allowable attenuation in the passband. So here what we need to do is, to calculate the poles of a Chebyshev filter, we need to make use of the formula phi k is equal to pi by 2 plus 2k minus 1 by 2n into pi. Just like what we did in a Butterworth filter, we can calculate the angles phi k, and rather than using cos phi k plus j sin phi k, because the poles are on an ellipse, we need to calculate sk is equal to a cos phi k plus j b sin phi k. From here, just like we find the poles, we should be able to find the denominator polynomial for the transfer function of the system. Now how to find the numerator depends on whether n is odd or n is even. From the denominator polynomial which you found, if n is odd, then you can put s is equal to 0 and whatever value you get, that is the value of the numerator. When n is even, if you substitute s is equal to 0, whatever you get, you need to divide the result by square root of 1 plus epsilon square. This is the value of the numerator. Let us take an example. Given the specifications, alpha p is equal to 3 dB and alpha s is equal to 16 dB, fp is equal to 1 kHz and fs is equal to 2 kHz, determine the order of the filter using Chebyshev approximation. From here, omega p is 2 pi into 1000 Hz, which is equal to 2000 pi. Omega s is equal to 2 pi into 2000, which is equal to 4000 pi radians per second, and alpha p is equal to 3 dB and alpha s is equal to 16 dB. So n is greater than equal to cos hyperbolic inverse of square root of 10 raised to power 0.1 alpha s minus 1 by 10 raised to power 0.1 alpha p minus 1 by cos hyperbolic inverse of omega s by omega p. If you substitute the values into this equation, you get n is equal to 1.91 and you need to round it off to 2. For n is even, you need to divide by is even, it starts by 1 upon square root of 1 plus epsilon square. Now you can find the values of the minor axis and the major axis as shown below. Epsilon is equal to 10 raised to power 0.1 alpha p minus 1 raised to power 0.5, so it comes out to be 1. Mu will come out to be 2.414. So A will come out to be 910 pi and B will be equal to 2197 pi respectively. The poles are given by Sk is equal to A cos phi k plus J B sin phi k for values of 135 degrees and 225 degrees. So S1 will come out to be minus 643.46 pi plus J 1554 pi and S2 will come out to be minus 643.46 pi minus j 1554 pi. The denominator thus is s plus 643.46 pi whole square plus 155.4 pi whole square. So the numerator and the denominator gives the given transfer function as shown. Let us take another example where you need to make a Chebyshev filter where 0.8 is less than equal to h of e raised to power j omega is less than 1. And absolute value of h of e raised to power j omega is less than equal to 0.2. From here, 1 upon square root of 1 plus lambda square should be equal to 0.2. So lambda comes out to be 4.899. 1 upon square root of 1 plus epsilon square is equal to 0.8. So epsilon comes out to be 0.75. Remember, we need to use bilinear transformation, and what we are given is digital frequency. So we need to warp the digital frequency using the formula omega p is equal to 2 by t tan of omega p by 2. So this comes out to be 0.6498, and omega s is equal to 2 by t tan of omega s by 2, which comes up by 2.752. Now n comes out to be cos hyperbolic inverse of lambda by epsilon by cos hyperbolic inverse of 1 by k, which is 1.208. So n becomes 2. So here mu becomes 3 and a is 0.3752, b is 0.75. So S1 is minus 0.2653 plus j 0.53. So denominator comes out to be s square plus 0.5306s plus 0.3516. So the numerator is 0.28. So HFS now becomes 0.28 by s square plus 0.5306s plus 0.3516. Remember, this is an analog transfer function. From this analog transfer function, supposing we want to get a digital transfer function, we need to substitute h of z, where s is equal to 2 by t, 1 minus z minus 1, 1 plus z minus 1. The moment you substitute this, you are going to get 0.052 1 plus z minus 1 whole square, 1 minus 1.3480 z minus 1 plus 0.608 z minus 2. Let us take another example where we got n is equal to 2 and we got the transfer function as shown below.